So cold, by the way. Okay, section 2.5, complex zeros and the fundamental theorem of algebra. Okay, classroom temperature is what, 61 degrees? No, it's not that cold. Is actually 68 degrees in here. Um, I will be able to, after this, use two major theorems, the fundamental theorem of algebra, the linear factorization theorem. Find complex conjugate zeros, and factor the real number coefficients. Is this complex conjugate zeros? Like we were working yesterday, the square root of 5, we had as a zero, this negative square root of 5, because we had to have that for integers to be our leading coefficients. Otherwise, they would have been irrational values of our leading coefficients for, no, I shouldn't say leading, but our coefficients with each one of our variables. So we have to have them in pairs, those factor pairs. So when we have square root as a a root or a zero, the negative square root or negative root of that side has to be part of our zeros. When we have a complex value, we have its complex conjugate as its pair. It has to be there, otherwise there should be an I in the polynomial as we're doing this. This is important because these topics provide the complete story about zeros and factors of polynomials with real number coefficients. Okay. Now, as we're moving on, two major theorems. These theorems are existence theorems. They tell us of the existence of zeros and linear factors, but not how to find them. Okay, they don't tell us how to find them, but they just tell, hey, they're out there. Okay, extraterrestrials, they're out there. Okay, a polynomial function of degree n has n complex zeros, real and non-real. Some of the zeros may be repeated. Okay. That's where we get that multiplicity idea as we review thinking about that. Linear factorization theorem, if f of x is a polynomial function of degree n greater than 0, okay? Remember, that's the largest degree in the polynomial, has precisely n linear factors, okay? And we can kind of figure that, x to the first power, x to the second power, and then we got to have, we should have just as many x's as there are degrees in your polynomials as far as your factors are concerned. So where a is the leading coefficient of f of x and z1, z2 to zn are the complex zeros. Now complex zeros are created when we have a zero that doesn't cross the x-axis. Okay? So keep that in mind. It's not crossing the axis, that's why the complex are created. The zi are not necessarily distinct numbers, some may be repeated. Basically, if you have a polynomial of degree n, you will have exactly n factors or zeros. This includes both real and non-real. That's why we talk about the ones that don't cross the axis are the imaginary ones. Fundamental polynomial connections in the complex case. The following statements about a polynomial function f are equivalent if k is a complex number. X equals k is a solution or root of the equation for f of x equals 0. Okay, so that's a 0. K is a 0 of the function, and x minus k is a factor of f of x. And if we're looking at the k, we're also talking about its conjugate as well. The only connection that is lost with the non-real zeros, they don't appear as x-intercepts in the graph. Okay? Creating a polynomial from its factors. Okay? Or its zeros for that matter. But here I got factors. Now, when I'm doing this, they got write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of its graph. Okay, so x-intercepts of the graph, so just what the zeros are, and then be able to multiply this out. So I've got that going on, I multiply. I got x squared minus 4i squared, but remember I is the square root of -1. So square root of -1 squared is just -1, so I got x squared plus 4. Now I've got my zeros. This has two zeros, x equals 2i and x equal -2i. The zeros are not real. The graph of f of x has no x-intercepts. Matter of fact, if you graph that puppy up, okay, it's a parabola that's 4 units above the x-axis, and a ain't crossing no axis, okay, because it's positive. And that's where we have this creation. Okay, if I ask you a question, when is this parabola positive? It's positive all the time. Okay, when is it negative? Never. Okay, so Just keep that in mind as we're doing this, because we're going to be learning something called sign charts. I think that's in section 2.8. It's kind of a neat thing, but we're talking about positive. When's it positive? When's it negative? When's it zero? Okay, and we're going to be looking at those types of things with inequalities. Now, when I'm looking at this next problem here, I've got f of x equals x minus 5 and x minus the square root of 2i and x plus the square root of 2i. I want to talk about a notation issue with these. You see how the I is kind of sandwiched to the square root of 2 there? And you know obviously it's not included underneath the square root. Do you see that? Because the square root does not extend over its top like it's a roof or awning to prevent it from getting wet in the rain, okay, or something to that effect. When you write it in your assignments, and depending on the assignment, you may see me, depending on, what I told students that day, that I will write it like that. So I'll go x plus I the square root of 2. I'll put it in front because that's obviously not underneath the square root. Okay, or I'll write it in such a way that it looks so obvious that it's not underneath the square root, it looks like I'm putting another value on there without a comma. Okay, but be very deliberate when you're writing your i's. Okay, not that you have to put a dot on top. Of course, if you don't, it looks like a 1. But be deliberate, because as you are combining like terms, you can open yourself up to making some silly mistakes because your notation was not as careful as you could be. Okay, so pay attention to that as we're going. But for right now, whenever I see that square root of an I, if I have an I in it, those are the ones I multiply together because they're conjugates. So they should disappear, right? So it'll be easier to multiply the other stuff in the problem later. So when I'm doing this first one, I'm really looking at this. I've got x minus 5, and I got x minus the square root of 2i, and this plus the square root of 2i. Well, the square root of 2, there's the difference of 2 squares. So I've got x squared plus 2, okay, because that I squared is negative 1. So I'm going to probably go a little slower just so you see that it's going to be this. And then I come up with this next thing here, and I have x plus 2. Okay, you all right? And it should be x squared. I apologize for not putting that in. X squared plus 2 as we're doing that. Are you okay with this so far? Now, when I do the distributive property on this, you could totally FOIL. But when it's more than just x, I have a tendency to screw it up. I do. So I'll either grab that lattice method that I showed you in class with that multiplication look, or I just distribute. Since it's a binomial and a binomial, this is what I generally tend to do. I've got x times x squared is x cubed, x times 2x plus 2x. Negative 5, x squared, and then I got a negative 10. And then based on that, I rearrange. Okay, but I always double check because I always have a tendency to make my little mistakes as I go, because I want x times x squared, x times 2x did that, negative 5 times x squared, negative 5 times 2. So now reorder. And make sure you name your function. Make sure you have function names in front of them. We're asked to write functions. Make sure you put a function name. F of s. S is x. Since these are f of x, that's why it's that name. I don't make up a new one. I just use the one that's current. If I'm creating one, f of x is great. S of x, whatever it is. But keep in mind, there are 3 zeros here. As I look at them, and I really should probably, well, I've got them right here, are 3 zeros. Of the 3, only x equals 5 is on the x-axis. You'll notice that the other ones kind of have a little wiggle, but they're above the axis in this case. Questions about that? Now, I prepped the board to make sure you guys know that's what I'm doing, and this is the reason why I'm prepping that board the way I do, okay? Because I want to be able to explain myself on the zeros. It's your turn. You guys got C. Give it a try. reason you're supposed to be doing the work, you know, you see. She's checking this video later. I'm picking on her a little bit. Get to 4. Now, as we're doing these, make sure you just pay attention. I got this x minus 3 and I've got that difference of 2 squares and I did them simultaneously type thing, okay, as I went. Now I'm just going to distribute that x squared plus 1 into both of them. So I've got this next step here that I've got going on. Notice all I did was x squared times x squared times 1. That's that first one. Wow, cool. Negative 6x times x squared is negative 6 cubed. Negative 6x times 1 is negative 6. 9 times x squared, 9 times 1. Now, after I do that setup, I do my combined like terms. Okay. And you notice that I did it earlier, but I'm checking it again. After you multiply, just double check you got your powers in there, you got the right variable in there, because there's a tendency to just forget. And then I combine like terms, and I get that done. And I should name my function when I'm done, f of x is equal to, so f of x has 3 zeros, I, negative I, and 3. By the way, its multiplicity is 2. That's where I put that m2. Since the only real root has multiplicity of 2, it touches but does not cross the x-axis. Okay, so you'll be asked, does it cross? Does it touch? And you got to just kind of remind yourself about the factors and the number of them. Okay. Now, after you finish writing that one down, you guys got the next one. Let's make sure that we're doing the multiplications and checking it out. Okay, and remember, group the things together. There is that pattern for the perfect cube that, to be honest, it's just easier and faster just to multiply the 3 together than do the perfect cube pattern, but it's v cubed minus 3u squared v, and then it's plus 3uv squared plus u cubed as you go through, but I find it's easier just to multiply them. Yeah, I remember that being 72 there. So the first one's really nice because I got the difference of 2 squares. So I've got x squared plus 9, okay, and it's weird being a difference of 2 squared and I get a plus 9, but remember it's an I squared. That's where that negative 1 comes in. And then the next one, I've got that set up. I just squared the first ones and I'm just going to do 2 more distributions on my work that I have. So keep in mind as we're going, I'm going to go with my x squared, my x minus 2 first. So my next one, I've got x squared plus 9. And I'm going to go x cubed minus 2x squared minus 4x squared plus 8x minus 8. I think I skipped something. X cubed, negative 2x, great, negative 4x squared. Negative 2 is positive 8x. Yeah, I forgot a 4x. Sorry about that. And then I can combine those like terms. X cubed, I got my 2x's minus 6x squared. And then I got plus 12x minus 8. And then I distribute that last one. I've got my x cubed and x squared, that's x to the 5th, plus 9x cubed, minus 6x to the 4th, minus 54x squared, plus 12x cubed, plus 108x, And then I got my 8 coming through, so I've got 8x squared plus 72, minus 72, excuse me. Let's slide that over a little bit. Pick some stuff up. That's got to be a minus 72, negative 72. Let's just rewrite that. Okay, then combining like terms, just to double check, I've got my x to the 5th, I got my 4, negative 6 to the 4th, and then I got my 3's. That's where my 21 comes from. I got my negative 54 plus 8. Ooh, was it a plus 8? Ooh, it's a minus 8. Boom. That's a minus 8 as you look through it. So I got negative 62x, 108x, minus 72. Okay, as we check through that. Clarification, we okay so far? Now, the nitpicky part of his notation, making sure you pay attention to negatives, okay, as we go through. But as we embark on this, we got our zeros, and the first zeros, the 5 zeros only real root has multiplicity of 3 across the x-axis and changes sign at x equal 2. That's why it crosses, it changes sign. Are we okay with that? Nice picture. Now we're going to talk about complex conjugates. So far we've just been doing imaginaries with single terms, and we've been noticing that they're positive and they have a negative, okay, when we've been working on them. When we work with the complex conjugates, we won't change the whole thing, we'll just change the imaginary portion of that when we set up that root, okay? So suppose that f of x is a polynomial function with real coefficients. And remember, this is about real coefficients. If a and b are real numbers with b not equal to 0 and a plus bi is a 0 of f of x, then its complex conjugate, a minus bi, is also a 0 of f of x. Okay, they come in pairs. Just like the square roots, they come in pairs. Okay, just like the other ones that we've been working with. So basically all non-real zeros occur in conjugate pairs. So when we set this up, I have this situation. Okay, notice how I said minimal degree. Okay, a lot of people will just look at that and go, okay, boom, I got x plus 5, I got x minus 3, and I got x minus 6i. I'm totally ready. And I'm like, wait a minute. You got a friend that you forgot, the conjugate. Okay, so as you're going through, don't forget about that. And your setup, once you do your setup, you're golden on this. You're just doing what we just did. Okay, so I'm going to multiply x plus 5 times x minus 3. And I've got x minus 6i and x plus 6i, which is beautiful because it's the difference of two squares, except that I put a plus sign between them, and that's going to be x squared plus 36. And I've got x squared plus 2x minus 15, and x squared plus 36. I'm going to multiply together in a second here. Now, if you were sitting in Mrs. Peterson's room, you would see her doing a multiplication of the square, doing the squares and then doing the 36, and she'll have two lines and she'll have you combine them and add them with two lines. You've seen me do the distributive property with the binomials to the trinomial, but you've also seen me do this. If I'm going to this, go x squared plus 2x, and I don't want to show the plus. If I got x squared, I got 2x, I got negative 15. And I've got x squared and 36, I can set it up like this and do kind of a lattice structure. And I'm just showing you on something smaller because you can do a trinomial, quadnomial, whatever size you want. It's a little easier because they're in boxes, okay? Because I just look at it like this. I combine the stuff across. Okay, so I've got x squared and x squared is x to the 4th. 2x is 2x cubed, negative 15x squared. I got 36x squared. 72x, and whatever 36 times 10, 360 and 5, 150, 180, 360 and 180 is 540. Negative 540 at the end there. Check me. I've been known to make mistakes. You do me a favor on that one and check me on that. Negative 15 times 36. Just you got the calculator in front of you. Is it 540? Good. Oh boy, you know, some people think I guess at those things. But after I do that, all my stuff, if it's gonna combine, you know, we'll kind of combine on the diagonal, but because of the different size powers, it's not as neat. So I got x to the fourth first. So my f of x to the fourth. Then I've got 2x cubed. I don't have anything else. 2x cubed. I've got x squared and x squared, 36 and 15, but 36 is positive, 15 is negative, so it's going to be positive 21x squared. And I got plus 72x minus 540. And I will move this all over so it's not all jumbled together, apparently. Okay. And we'll check to make sure I was happy with that because I did it earlier and I just want to make sure, okay, that I'm not giving you guys a bunch of junk. But keep in mind, you have choices. Your choice is based on, really, your most common mistake. Okay? I mean, think about the mistakes you'd make when you're doing this type of multiplication because they're, you know, just one mistake, you know, it's a half point, it's a point, depending on how many times that mistake, you know, multiplies throughout your problem. I try to follow them through, you know, as I go through. That's why you'll see me actually write out the entire solution because I'm following your mistake through after I'm done. Okay, I just want to make sure you recognize it as you go. And after you finish, just like any good geometry student, reread your question. Make sure you answered all the things you're supposed to. So find a polynomial function with integer coefficients with minimal degree, and so we've taken care of it. But the thing I want to make sure that we're doing, a lot of times I'm seeing people give me answers without the name of the function. Please put a function name in there. It was f of x at the start, or, you know, so I'm staying consistent. Your turn. You all got example 2. Go for it. Now remember, you have a conjugate to consider. Your conjugate consideration, you should be also looking at this as a factor. Now I got some folks right now that are in it and they're like, okay, I got it, but are you at least to the setup? Now, I'm going to reprise the idea of a shortcut a little bit. I'm going to multiply x plus 3 and x minus 4, okay, as I go. And no, actually, I think I can do that. This is going to be x squared, and I've got negative x, negative 12. But now this next thing here that I'm going to do freaks people out because I jumped right to this. And I want to talk about what I did. So here's the deal. Right? Because if I distribute my negative, this is going to be x minus 2 plus I. And if I distribute the negative in this next one, I've got x minus 2 minus I. Are you in agreement so far? Okay. All I did was distribute the negative here. Maybe this is kind of confusing. But I took this there and there, and I took this there and there. Now folks are like, well, what's the deal about that, Bloom? I'm doing a difference of 2 squares. Okay. I've got a complex conjugate, okay, and each time I introduce this, I'm going to have this situation of a difference of 2 squares. I got x minus 2 and x minus 2 squared, okay? So let's talk about that. I know that's my answer, but I'll show you what I did. I got x squared minus 4x plus 4. That's x minus 2 squared. Are you in agreement? Because it was the difference of 2 squared, I just squared x minus 2. Now, my inside-outside terms should knock out because of the plus and minus. And now I just square the end terms, which both happen to be positive I and negative I, right? So I multiply those together. I get negative I squared, which is just 1. So I add in the plus 1. Okay? I end up doing this quite quickly because of the pattern that exists in the problem. Does that make sense? Do you see how I'm doing it, yay or nay? Follow-up questions? I got some really thoughtful looks at this. They're not puzzled, scrunched up faces, so I'm feeling like you guys get what I did when I did my chalk talk. But if I notice some patterns to help me, I didn't change the problem. I just noticed the pattern to multiply faster. Okay? But now, if you didn't notice it and you just went through and multiplied, you should end up being after the second step right here, and I'm going to combine like terms, and now I've got the issue of multiplying that. So I ain't going to be shy about it. I'm going right to a lattice, you know, that multiplication box, because that is way easier for me after I go 2 and 2. I might be able to distribute a 3 and 2, but not a 3 and a 3. Okay, it's just much easier for me to do it this way. And it takes less room than doing the columns. You can, but that column thing, by multiplying that first term to everything, the second term to everything, and adjusting and then adding in the rows. Okay, so, or I should say adding in the columns. So I'm just taking care of it. And notice, because they're consistent squared first, no power, 2, 1, 0, the diagonals, when I combine them, are where it's at. So my final answer should be f of x is equal to x to the fourth minus 5x cubed minus 3x squared plus 43x minus 60. Double check, don't take it out of word, because with all that, one sign error. You gotta be careful with your signs. Okay, people are always like, well, how often do you do it? I do it on the board, I do it separately, prepping, and then I do it again the morning that I'm doing this, just to make sure that I don't make a sign error, so I'm not wasting your time. Okay, so I kind of know what's going on as I go, but if you guys notice one as I'm doing it free, pay it, just pipe up. Is it making sense? Okay, now, remember, we got a conjugate that has to come along with this. We have pairs when we talk about i's, any type of imaginary number, or square roots. Okay, so now, write a polynomial function of minimum degree in standard form with real coefficients whose zeros include, but are not limited to, go ahead, give it a try. This is our practice. If you're wondering what a test question may be like, it's here. Okay. By the way, the Chapter 2 Part B test has 8 questions, including the extra credit. So 7 questions is it. One of the questions is worth 15 points. We haven't done the work to give you an idea what that question might be like. The remainder of the questions are anywhere from 4 to 10 points. Okay, so keep that in mind. It is a very short test, but it will take the time. Okay. And that test was cut down from last year, I think, or 2 years ago, which was it was a 10 or 11 question test. So make sure you're on the right trail. That should be your initial setup. Okay, check it out. Now the remainders, nitpicky. Do them. Make sure you're doing it in pencil. If anybody needs a pencil, I will deliver a pencil. Okay, if you're at home, I'm not doing that. But if you're here on campus, I will deliver a pencil. I want to make sure you get an opportunity to practice this. This is very much like a test question. Use that difference of 2 squares trick with the grouping. It'll make it faster. Plague girl. Hey, that's funny. You're PG. Focus, 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 focus. Yeah. Again, I grouped it. That's the opposite. I grouped it. That's an opposite. I grouped it. That's an opposite. I grouped it. That's an opposite. So I'm using that difference of two squares idea. Okay. I take my first term, x minus 1, I square it. X minus 1 times x minus 1 is x squared minus 2x plus 1. Then I look at this term. I got negative 2i plus 2 times 2i, which is negative 4i squared, which is positive 4. And that's where that came from. Again, that covers these two. Then I look at this one. I got that x minus 1 again, and x minus 1, well, that's x squared minus 2x plus 1. It's the same as this one was, okay, because it's the same forward setup. Then I've got minus I and plus I, right? That's negative I squared, but it's I squared is negative 1, positive 1, and that's where that came from. Okay, so it allowed me to multiply faster because I used my patterns that I recognized as I go. Okay, I'm just using the difference of two squares, and I'm using the perfect square pattern and the difference of two square patterns to get it done. After I do that, I combine the terms that were funky, and now I got a lattice in x1. I've just multiplied x minus 1 times 1, and now I just set up my multiplication lattice for my next thing. I got x squared minus 2x plus 2. And then I go ahead and get that done after I get to this spot. Not sure why I repeated that twice. Did I just combine like terms? Oh, I combined my like terms. And I get that. Yep. By the way, the practice on our elk time after we do completing the square, writing a vertex form, and given 2 points writing the vertex form, we're going to be creating polynomials from factors, and those are the factors we're working on. Okay, just more practice. Might even be the same couple questions or a couple more from your assignment. Okay, so just know I'm recognizing other ways, other patterns to help me multiply. Just like yesterday when we were doing that synthetic division, I just pulled out a factor and said, hey, look, it's the difference of two squares, so I can make my synthetic division multiplication faster. Okay, same idea here. It's just about taking things you already knew from Expo, literally Expo and algebra from 8th grade, and just reiterating those patterns that we practice in Chapter P. Okay. We're going to hang on to example 4. We'll stop here. Questions regarding the pattern. I'm okay with discussing it. I'm okay with doing it again. I'll do it free as well if you want to see it again. Okay, yeah. To going over the grouping? Okay, so now keep in mind, I got to get it to a difference of two squares, right? You darn thing, I can't do it that way. Hold on a second. It's like, I can do all sorts of stuff. Let's do this. Let's get rid of those. So we're here. Now remember, it's best if I can get it into a difference of two squares, right? I mean, I may not always, and I'll deal with it. But in this particular case, I'm looking at the fact, and I'm just letting that one sit there, and I'm going to get a different color. I have x minus 1 minus 2i. I have x minus 1 plus 2i. I have x minus 1 plus I, and x minus 1 minus I. Okay, and I still got x minus 1 over here. Okay, but now, keep in mind, this is the same as that. This is the same as that. Are you okay with that? But now when I group those, I think those, hey, let's pretend they're y's for a second. I have, in this one, I have the difference of two squares, right? So I'm using that to my advantage. Because x minus 1 squared, I can do in my head. I mean, because that's x minus, because my outside and inside knock each other out. And then I got my last squared, I squared. I mean, but I'm thinking about this in my head. So now I've got x squared minus 2x plus 1 plus 4, because that's what that's going to be. And so my next line, I could just go like this, plus 5, x minus 1. Okay? Do you see where I'm doing it? And the thing is, I'm going to tell you, I haven't done it a lot. When I first started teaching this course, I was like, what? And I was like, oh, that's so cool, because you're just really bringing it down to the difference of two squares, and I know that pattern. You know, I've done a ton of them. So let's look at this next one, same idea, and it is, as we go through, I've got x minus 1 squared, and I just did that, so I got x squared minus 2x, because, you know, inside, outside, add, and then I've got plus 1. Well, that's my first, right? My outside and inside and the difference of two squares knock each other out. My last squared, negative I squared. Well, that's going to be x squared minus 2x plus 1 plus 1. And that's where this value comes from. There, I'm going to multiply that times that for my f of x. I'm not quite done, but that's the steps that I would take to get to that point. Because after that, it's not as alien looking, okay? But you got to keep in mind the pattern that I'm doing. Those patterns exist to make things faster for us. When you're an expo student, when you're a algebra 2, when you're a algebra student, you know, and when you guys had it in middle school, you know, you don't notice them. You're like, yeah, these patterns, yeah, whatever, boom, you know. But when you're here, can you see the power of the pattern? I mean, that thing rocked. And instead of showing all this, I can go straight to those without even batting an eye, so long as I group them right. So it's me paying attention to grouping, but remember, I'm not changing the value. I'm not doing creative mathematics. These are actual values that I'm squaring. I squared x minus 1. It's x squared minus 2x plus 1. Okay? And then I do the rest, and it's first, outside, inside, last. That's all I'm really doing. But it's the difference of two squares pattern. Okay? What's really cool in these conjugate things, it's always there. It's something I use. And you'll notice I use it on the assignment a lot. And you're like, how did he do that? Just practice them. It makes you better at it. Okay? So just be patient. If you got questions, I'm more than happy, because I'm also aware that Lord knows if I could only be perfect, okay? So just keep in mind, if you do notice any mistakes, that you just point them out to me, okay? Thanks for your time today, folks. I really greatly appreciate it.